The diagram shows a wedge, all of whose faces are smooth, resting on a smooth horizontal table. Its faces make an angle A and B with the table where tan of A is equal to 4/3 and tan of B is equal to 3/4. And particles, each of mass m, are placed on these faces. And if the mass of the wedge itself is 2m, shows the wedge will not move. Now you draw your wedge, put the two masses on it, you draw the normal force in. Notice the normal force for the tip and particles, because they're going different directions, even though they're the same weight, they're different. Call this one R, this one S, or any letter you choose. We know the force of this mass is mg, that's its weight coming down. We're trying to divide it into its perpendicular and parallel components. That's important. For the mass and the particle, we're trying to break down its force into its perpendicular and parallel forces. The same with the mass on this side of the wedge. We're trying to break it. Its mass comes straight down to, that's its mg, comes down this way, and we're breaking it into its parallel and perpendicular and parallel components. The next thing we do is you look at the angle A, and we're told that I think tan of A is equal to 4/3, so we can fill in our hypotenuse as well. So now we know what sine and cosine of those at that angle A will be. Similarly with B, we're told that I think tan B is equal to 3/4, so we complete our triangle to make this 5, and again equally we can work out sine and cosine of that. So let's do that. We know that this particular angle, this length here, is cosine of mg. So cosine is equal to adjacent over hypotenuse, which is 3/5, so it's 3/5 mg, and sine is equal to 4/5 mg. On the S side over here, cosine is equal to adjacent over hypotenuse, which is 4. So this is the cosine side, which is 4/5 mg, and this is the sine side, which is 3/5 mg. And now that we have the forces done, let's put the accelerations in place. So the dotted line represents the acceleration of the wedge, and that's A. We're looking for the acceleration of the particle parallel to the incline, to the slope, and perpendicular. Same as we were with the forces. We want the accelerations to be parallel and perpendicular. So we have the F acceleration, which is the acceleration of the particle directly coming down, and then we break down A into its cosine and sine components. This is the angle A, and this is the cosine component, which is 3/5, which is adjacent over hypotenuse, which is 3/5a, and this is your sine, which is 4/5a. Now we look at the second particle. Our acceleration for the wedge is still A, and we're still kind of thinking that it's moving in a direction from west to east. We're going this way. So we're looking for the acceleration of our particle to be parallel to this plane and also perpendicular to the plane. So since the acceleration of the wedge is going from west to east, equally, when we break down the acceleration of our particle, it should be going kind of from an east to west direction as well. So, it's not going to be going this direction here, for example. That will not be going this direction, because that will be from east to west, which would be the wrong direction. So in general, it's going to be that way. This angle B, I've identified that B here, I've identified that B here. Let's see why that is B. What I'm saying is that this angle here is B. Because if this here is B, and this is a 90, and this is a 90-degree angle coming down to here, because it's dropping perpendicular down to the base, well then this has to be 90 minus B, that angle there that I'm just making green. And if that's 90 minus B in there, okay, and this is 90, well then this angle here that I'm now pointing at in blue, this must be B. So you can experiment with that yourself to have a look, but that's B. So this angle is B, and therefore this angle here is the cosine. So it's going to be cosine of B, which is equal to 4/5. So that's going to be 4/5a, and this is your sine, 3/5. Very simply, by the way, if you just rotate this whole angle here, if you rotate this triangle here to 90 degrees anti-clockwise, you'll get your dotted line going across, and you get your arrows pointing in the right direction, just to help you draw it. One other force I haven't mentioned is the force H coming down, which is the force of the particle itself coming straight down the slope. Now let's use those forces and accelerations of the different particles to work out the parallel force and perpendicular force for each one of them. So we're going to get four different formula here. So parallel of the first particle. So our force parallel is 4/5 mg is equal to our mass by our acceleration. There's no more parallel forces. So our 4/5 mg is equal to our mass, which is m, and our acceleration is equal to f minus 3/5 a. Now on the perpendicular side, we have 3/5 mg minus r is equal to the mass, which is m, and our acceleration is equal to 4/5 a. So there we are, 3/5 mg minus r is equal to our mass by the acceleration, which is, there's our acceleration, 4/5 a. Rewriting that, I'm going to get r is equal to 3/5 mg minus 4/5 a. So that's r. We're going to need that in a little bit. Let's look at the second particle now. So parallel, F is equal to ma. So parallel is going to be 3/5 mg is equal to the mass, and the acceleration is equal to, let's look at our acceleration, is h plus 4/5 of a. Okay, so h plus 4/5, that's the acceleration going in this direction. And perpendicular, we're going to have 4/5 mg minus s is equal to the mass, and the acceleration in the perpendicular direction is equal to 3/5 a. So s minus 4/5 mg, and that's equal to mass by the acceleration in the perpendicular direction, which is 3/5 a. And I rewrite that in terms of s. S is equal to 3/5 ma plus 4/5 mg. Now we have to do the wedge. Let's have a look at the wedge. So here's our wedge down here. I might just make it a bit bigger. So on the wedge, we draw our two masses. We put in the normal force R and S, and we now need to break it down into a horizontal direction. We need to break it down into horizontal direction. The wedge only potentially moves in a horizontal direction, and so we need to break down our normal forces into the vertical and horizontal components. So this here is the sine component, so it's going to be 4/5 of r, and it's pointing in this direction because this mass will be going this direction. And this mass here, we break down into its vertical and horizontal, and it's equal, this sine of b is equal to 3/5 s. So our force is equal to mass by acceleration. Force is equal to 4/5 r minus 3/5 s is equal to 2 mass by acceleration, 2m. Well, the mass of the whole wedge is equal to 2m by acceleration. Now what I do is I replace this r in instead of r here, and I replace this s here in instead of this s here. And then I multiply it all out. You can follow this yourself. You can see that things like this is going to cancel out here, and you're left with minus 25a is equal to 2a, minus 25 over 25. So minus a is equal to 2a. And if in that situation, the only solution is that a is equal to 0. So the acceleration is equal to 0, therefore the wedge doesn't move. And therefore you've proved what you were asked to prove at the start of this question. Show that the wedge will not move. So we've done that. Just a quick note on acceleration. This particular question, we assumed that the acceleration was going from west to east. What would if we assumed that it was going from east to west, going in this direction? Well, in that case, we'd have this diagram here, or acceleration, or dotted line would be still coming across, but now we're implying it's going to go this way. And that means that this arrow would be pointing upwards, and this would be coming down. So that would be different. So we'd have our acceleration here would be f plus 3/5 a in the parallel direction, and so it just changes direction. What would happen here if this a was traveling in this direction? Well, then we're going to find that that's going from an east to west, so this arrow would be coming down in a easterly westerly direction, and this would be traveling up. Okay, the h would still be traveling down because that's just the particle kind of sliding down this plane, but as you can see, everything is reversed. I haven't done it, but if we did make that assumption and then we followed on and did all of our formulae, it will of course work out the same. Well, it should work out the same. That the that the wedge doesn't move. One final point. Down here when we had force is equal to mass by acceleration, and we said 4/5 mg is equal to f is equal to the mass, and then the acceleration we said f minus 3.5a. That's making an assumption that the main acceleration is going this way. F is this positive direction, and the 3/5 a is going the opposite direction. Okay, so why do we assume instead of 3/5 a minus f? Well, the reason is because the force in the parallel direction is going this way. So that's our force. that's our acceleration as well. So we've got our 4/5 mg as our force, and then our F, which is our acceleration, is going this way too. So that's why they must be going the same direction. Okay.